trust me. And then there was another.
All right, let's get started. Any Parks and Rec fans out there? Nobody likes Parks and Rec.
I love that.
They like saving.
I don't know why.
All right. So, exam corrections. If you have not done so, right now. Okay. Attendance grades on Blackboard are up to date. You have your exam corrections turned in right now, so I haven't reported the exam grades. If I don't have your exam corrections, your original grade stands, and you all know the drill. Homework 5 is due on Wednesday, so today is the last day of lecture before you turn that in. Does anybody have any questions about homework 5? You should be able to do all of that, but we don't have any lingering topics. Any questions at all? All right. Okay, so what we're going to do today is, I mean, not to add any melodramatic flair, but we're probably going to start, what many students consider to be the trickiest topic of the class, which is the design for shear. Okay, because the design for shear is a little different. It's not the same as with moment. With moment, from a procedural standpoint, ultimately what you're kind of doing is solving for X. You know, you do all this stuff and you figure out, okay, here's how much steel you need, pick a pattern. Here's the required beam width, pick a size. Shear's a little different because it's graphical and it's iterative. Like you have to follow it through the entire length of the span. So it's a little different. I want to sort of set the stage. We're going to break out some stuff regarding Moore's circle, which I know that for many of you, I even remember when I was an undergrad, Moore's circle was kind of a weird topic to understand. So we're going to take our time with it. I think that the math is pretty simple. Ultimately, with shear design, you don't really need to go back and check your design because of the nature of the problem. But there's a little bit, there's some stuff going on that I think we kind of need to understand. So let's go back to this. Let's go back to basics. So I have a beam here, simply supported beam, uniformly distributed load. You all should be able to draw that, right? I would hope so. And the moment diagram, so it's a parabola, it's curved downward. And what's the maximum moment on that moment diagram?
WL squared over 8.
There we go, WL squared over 8. That's exactly right. And so ultimately, up until now, that's all we've cared about. And we've been talking about this for a long time. I mean, almost half of the semester has been devoted to just that, to the moments on the beam. But you should know that's not it. There's a whole bunch of other stuff going on. We have deflections, which we're going to consider later, but we also have shears, right? There is a shear distribution on the beam, and now we need to talk about that. We need to talk about designing the beam to resist shear, okay? And what I'm talking about are the stirrups, okay? I've shown you this image before a couple times throughout lecture. What I have here is a typical reinforcement layout in a reinforced concrete beam, okay? And if you look at this reinforcement layout, each of the bars have a specific function, okay? For example, these bars here are the tensile reinforcement, right? You take the beam, you apply load to it, it bends in a smiley face, positive bending fashion. So the top of the beam is experiencing compression, the bottom is experiencing tension. So these bars here that are going like that, those are the bars that are primarily resisting the moment. Okay, so I have tensile reinforcement on the bottom, and I went ahead and threw some compressive reinforcement up top. I don't necessarily always have to have it, but I can count on it if it's there. That compressive reinforcement, not only can it resist load, but it also tends or serves to tie together all of the reinforcement in the beam. The rest of the reinforcement, these little hoop things going on here, are what we call stirrups. Okay, And those stirrups are there for a very particular reason. Those stirrups are there to resist the beam's shear forces. Okay? And so what we're going to talk about here is how to design the stirrup pattern in a reinforced concrete section. But in order to do that, we kind of have to talk a little bit about some behavioral aspects. Okay, now we're going to go back to Engineering 216. It's probably been a long time since you've talked about this. And even then, when you talk about this, the idea of Moore's circle was always a topic that's usually a little confusing. Okay, so how many of you kind of at least remember Moore's circle or kind of know what I'm talking about? Okay. Now, Moore's circle, when it is first presented to you, is presented in a somewhat complicated trigonometric, geometric derivation. Okay? I tend to explain it a little more simply. Okay? You got your karate chop, you got your judo chop, you got your ninja chop, right? Now, you don't go karate chopping while you're kung fu kicking, right? You go like that. There goes your legs. Anybody get the reference? Does anybody get? Okay, somebody gets the reference. Thank you. Google it. You'll get it. I'm joking. In all seriousness, all Moore's circle is an analytical tool that we use to assess what are the stresses when we cut a section at a different angle. For instance, I have a bar. I'm yanking on it. Okay, so what is the stress? Let's see if anybody remembers this. What if I have a bar, I'm yanking on it, what's the stress?
P over area.
P over A. Exactly right. Now, that section cut assumes that I'm doing that. In other words, I'm cutting normal to the axis of loading. Okay? But what if, instead of a judo chop, I do a karate chop? What if I cut it at some angle? Well, if you cut it at an angle, you're going to get different stresses, right? Namely, if you cut it at an angle, what will happen is you'll get, so if I, here's the section, and I'm yanking on it, and I cut it at some angle, I'm going to get some normal stress component and some shear stress component. Now, if all you're doing is yanking on it, to be honest, that doesn't really make a lot of sense. Okay? Because the absolute worst case scenario is to cut it, at 90 degrees. But what if I don't have just an axial load? What if I'm taking it and I'm pulling it and I'm twisting it and I'm bending it and I'm shearing it and I'm doing all these different things to it? One of the critical components of stress analysis is to try and figure out exactly that. What is that worst case orientation? Okay? What is Moore's circle? It's just, that's all it is. Okay? It's trying to figure out the worst case orientation, and ultimately, a Moore's circle analysis, the goal is to try and determine what are called principal stresses. Okay? So what is the worst case orientation, and what are the stresses at that orientation? That's Moore's circle in a nutshell. Okay? So let me see if let me Google something. Let me see if I can find this. Here we go. So what you're seeing here, this is a video I kind of like to show in deformables. So what? Oh, pause it. Okay. So what you're seeing here is a state of stress. So let's take an element. Let's say I'm yanking on it in the X direction. I'm yanking on it in the Y direction, and I'm shearing it. Okay? What you're seeing are the changing stresses as you rotate the way you cut it. Maybe cut it this way, or this way, or this way, or this way, or this way. And so as you change that orientation, you're getting different resulting stresses. Okay? Now, what happens is this. Okay? So let me pause it right there. Okay, so let's say I've cut it at an angle of 9.92 degrees. Okay, now this, I'm not trying to teach you all the math behind all of this. Okay, if we were in Engineering 216, we would go through and derive it, and that's sort of one of the purposes of this class. I'm not trying to do that in here. I just want you to try and understand the concept. Okay, so at an orientation, let's say of 9.92 degrees, I have a normal stress in the x direction of about negative 80, we'll say negative 80 KSI. So when it says negative 80, that means compression. We have a stress in the y direction, a positive stress of 10.9 KSI, so that's in tension. And then we have a shear stress of 122. Now that's at an angle of 9.92 degrees. If I cut it at another angle, maybe here, now the stress has changed. I get an axial stress of negative 30, an axial stress of negative 39, and this is 131. See what's happening? Now what I want you to do is I want you to pay attention to the shear stress. Okay? Now, if you notice, I'm sorry, I want to mention this. If you notice the plot, see these green lines here and these red lines here? This is, this would be the stress in the x direction. Notice it's really small, so there's not really a line. This is the stress in the y direction, and these are the shear stresses. So let me play through this. And I want you to sort of pay attention to the shear stresses. See how they're starting to get small? Right about there. That's about the best I can do with my quick draw hitting the pause button. Okay? So this is about where the shear stress is 0. Now one of the things you'll notice is that, and this is sort of a hallmark of a Mohr circle analysis or of just stresses in 2 dimensions, whenever the shear stress is 0, the normal stresses are at their maximum. Okay? So you'll just sort of look at the values and watch them. You'll see as the shear stress drops, the normal stress gets larger. And you're going to see where I'm going with this here in a second. So, and see, look, watch. Now the shear stress is getting higher, the normal stresses are getting lower. Is everybody kind of seeing that? Okay. All right. So what we say in a Mohr circle analysis is that when the shear stresses, let's see, oh, let's get back here. When the shear stresses hit 0, about like that, your normal stresses reach their maximum. We have a name for that. We call those principal stresses. Okay? And usually when you're designing, you kind of design looking at your principal stresses. Your principal stresses being the worst case orientation of your stress state. Now where does that come into effect here? Here's where this comes into effect. Okay? Now, like I said, I'm not trying to get you all to memorize or do all of this Mohr circle math. That's what Engineering 216 is for. You've already done that. I just want to remind you of what's going on and talk about the case that I am interested in, which is this. Okay? This is a stress state of pure shear. Okay? We're talking about shear. So, let's see where that's relevant. Okay, so let's say I have a state that has 0 stress in the x direction, 0 stress in the y direction, but I have a state of pure shear. What Mohr's circle tells us is that what orientation gives us the worst case scenario? It's an orientation of 45 degrees. At that orientation of 45 degrees, what happens is you get tension this way and you get compression this way. So you're like your sigma x might be this, your sigma y might be that, and your shear stress is 0. Now, I'm looking here at tension and compression. What's going on with concrete and compression and tension? Remind me. If I'm talking about concrete and its behavior in compression versus its behavior in tension, what can you tell me about that?
Tension is trash.
There we go. Concrete is a material that behaves very poorly in tension, but it behaves very well in compression. Well, under a state of pure shear, the worst case scenario is at a section of 45 degrees. Here's what happens when a concrete beam is subjected to pure shear. It fails like this. Why does it fail like this? Well, this angle is 45 degrees. At this section, again, this is the ninja chop way of looking at the section. What happens? I have tension this way. The beam is wanting to open up in this direction. Why is it cracking at a 45 degree angle in shear? It's because of Mohr circle. Mohr circle states that when you have a section subjected to pure shear, it wants to fail, or its principal stresses are at a 45 degree angle. At that 45-degree angle, we have tension this way, compression this way, so the concrete is wanting to open this way, hence why it cracks like this, okay? And I'm showing you this for a couple reasons. First reason I'm showing you is because I want you to be aware of the behavior. Second reason I want to show you is because I just want you all just to have a factoid tidbit about concrete. When we look at a tension-controlled beam, you know, in other words, remember what's the difference between tension-controlled and compression-controlled? Remember, tension-controlled, the beam fails, the rebar fails before the concrete does, right? Tension-controlled beams fail ductily. In other words, they exhibit a lot of deformation before failure. There's a lot of warning. So in moment, usually in practical aspects, in moment, beams fail pretty ductily. There's a lot of warning before failure. But in shear, beams do not fail that way. They fail in a brittle mode. If you're ever on a construction site and you see cracks like this near the support, you get everybody the hell out of there, because when a concrete beam fails in shear, it goes quick. Okay, so that's just something to be aware of from a behavioral standpoint. If you ever watch a concrete test in shear, you see nothing, boom, it's gone. So just, if you ever see a shear crack, move. So just factoids, tidbits for the future. Okay, anybody have any questions? All right, let's talk about the math. First off, one of the things about shear is that by its very nature, the behavior surrounding its equations are a lot easier to understand. So, for example, how have we been doing, like all the expressions that we've been using for moment capacity have basically been some force times some moment arc. So we've been using that fundamental principle of statics. Well, we're not doing that here. We're not talking about sum of moments. We're talking about sum of forces, okay? So here's the thing. When you have a shear diagram, remember, what is a shear diagram from structural analysis? All a shear diagram is a visual representation of the sum of forces in the y direction, right? Remember when you start plotting a shear diagram, you start at 0, and then when it's all said and done, you better end back at 0 in one way, shape, or form? All it is just a fancy graphical representation of the fact that equilibrium is maintained, that the sum of forces in the y direction equals 0, okay? So here's the easy way of thinking about it, okay? I have some force acting downward on the beam. So the beam must resist that through an equal and opposite, force. So I propose that the nominal capacity in shear is whatever I'm getting from the concrete plus whatever I'm getting from the steel. It's that simple, okay? So how do we determine the nominal capacity? It's just the nominal capacity provided by the concrete plus the nominal capacity provided by the shear. That's it. Okay, that's simple. So that's point one. Point two, remember how with beams we had to go through this protracted procedure to figure out what phi is? Well, the reason why was because in beams, the determination of our resistance factor was a function of the strain in the steel. In other words, that strain in the steel helped us determine whether or not we were dealing with a compression-controlled section, a tension-controlled section, or something in the transition region. We're not having to worry about that here. For shear, because we're dealing with just sum of forces in the x direction, we're not having to deal with like strain determinations. Phi is just a constant 0.75. So for this entire aspect of shear, phi is a constant. It's just 0.75. That's it. But it's a lot easier from that perspective. The math is a little bit more doable. Okay, so our nominal capacity is the nominal capacity provided by the concrete plus the nominal capacity provided by the steel. So let's take each of these one at a time. Let's start off with the nominal capacity of the concrete. Okay, so the formula that we're going to use is this one right here. Now, first off, I see a square root of FC prime. What's going on with that? Whenever I see a square root of FC prime,
PSI.
You put in PSI, you get out PSI, okay? So there is that. So when I compute VC, my initial answer will probably be in pounds, all right? Because I'll take a B that is in inches, a D that's in inches, 2 lambda BD squared root of FC prime, the answer will come out in pounds. Now, everything else that you see in that formula, you should have already seen at some point or another, right? BW and D, those are beam dimensions. Lambda, now we haven't dealt with lambda in a little while, but that's the same lambda that we dealt with before, that lightweight aggregate factor. Remember, if we were dealing with lightweight concrete, lambda was 0.75, regular old everyday concrete, lambda is 1. Okay? Now, that equation up top is the equation we're going to use in this class. I thought that I would be remiss if I didn't mention what's going on in the gray box. According to our new version of ACI, ACI actually provides a more refined means of computing BC, and you can optionally use either one. There is a reason for the second equation though, and I kind of want to explain. The capacity of a beam in shear is a function of the size of the web, okay? So if you have here's a very, very basic behavioral observation in beams. Like if I have a concrete beam that looks, let's say like that. Let's say it's an I-beam. And this is the same behavioral observation in steel design, by the way. Like when we look at the shear capacity of steel beams, it's going to be very similar in this regard. But I'm getting ahead of myself. When you have a beam that looks something like this, a very, very simple way of looking at it is to say that the moment, its moment capacity, its capacity to resist bending, is primarily resisted by the flanges, but its shear capacity is defined by the web, okay? So when you look at the expression for BC, a lot of these are a function of the web, the width of the web. D is how deep it is. So you can kind of think of it as the shear capacity of the beam is sort of defined by that region there, if that makes any sense. Everybody okay with that? Now, what's going on in the gray box? This is, again, I'm not going to make you memorize this for an exam or anything. Don't worry. I just want you to have an understanding as to why that gray box is there. It would stand to reason that if I had a beam and I doubled its depth, that I would double its capacity, right? That would make sense. It actually doesn't work out that way. When concrete beams get really, really, uber deep, their capacity doesn't double. It actually sort of peters off a bit. When you have really, really deep sections, their behavior gets a little wonky. That equation in the gray box is a little bit of a more refined expression to help capture that effect. But for regular old, normal, everyday concrete design, you really don't need to worry about it. The spec gives you the option of assessing both. I really don't think you'd get a big change in a regular old beam design from using one or the other. It's only when you have a really deep beam that you really want to consider using that. So for our purposes, we really don't need to worry about it. Okay, so that's the shear capacity provided by the concrete. What about the shear capacity provided by the steel? And when I say the steel, I mean the stirrups. I'm talking about those hoop sections going across the span. Now, this is where things get a little new. Okay, so I want you to sort of pay attention to some of these terms. It's not the math that's complicated. It's figuring out the right terms going into it. So the capacity from the stirrups is calculated by multiplying the area of shear reinforcement, okay, the yield stress of the shear reinforcement, and then the number of bars per depth, okay? So the way that we compute that is D over S, okay? I'll give you all a sec to write this down. I want to explain what each of these terms are and why they are what they are. Very good? I see a couple people still writing. Okay. The first thing I want to explain is this term D over S. This term D over S is sort of trying to figure out how many stirrups cross a given crack. Okay? So let's say, for the sake of discussion, that you're going to have to bear with my artwork here, but let's say that here's my beam. I've got my reinforcement right here. Here's my stirrup. And let's say, for the sake of discussion, that this is 24 inches. So that's D. D is 24 inches. Okay? Now, if I look at the beam like that, what am I going to see? I'm going to see a beam that's like that. These are, so this right here, those are the longitudinal reinforcements, and these are the stirrups, right? Okay, now remind me, how does a concrete beam fail in shear? What's the angle of the crack?
45 degrees.
45 degrees. Okay, so let's say that I have a cracked section. So here's my support. And let's say it cracked at about 45 degrees. So the section looks something about like this. Okay, now remind me, this dimension here is still 24 inches from the top of the beam to this reinforcement. And let's take a look at this region here. If I assume that's 45 degrees, this is also going to be 24 inches, right? From that point to the top of the section, right? The idea is this term D over S, that term tells us how many stirrups cross a given cracked region. Like, let's say that this spacing right here, let's say that S is 6 inches, okay? If it is, say, 6 inches, I could assume that across a crack that's 24 inches wide, I'm probably going to have 1, 2, 3, 4 stirrups cross that crack. So does that make sense? And so why am I getting 4 stirrups? Because it's 24 inches over 6 inches. Does that make sense? So from a capacity standpoint, I'm taking the area of steel times the yield stress times D over S. Why D over S? Because D over S is a reasonable estimate of about how many stirrups would cross a 45-degree crack. That makes sense? I mean, without those stirrups, once you hit BC, boom, it fails, right? But once you pass BC, what's preventing this beam from falling in the river? It's these stirrups holding everything together, right? Does that make sense? Okay. So why do we use D over S? It's that. Now, the only other thing that's complicated is the AV term. Okay? There's no way I could draw that image as well on the board, which is why I'm just going to rely on the screen. Okay? So I have here an image of a reinforced concrete beam, and the beam has undergone a 45-degree crack. And what I'm doing is I'm looking at the beam in an isometric view, right? So everything that you see here is sort of the same that you see here, but it's in 3 dimensions. So these 2 bars here, those are my longitudinal reinforcement along the span, and then these are the stirrups, right? So in this image, I don't have 4 stirrups across a crack, I have 2, right? But the thing to keep in mind is that across the crack, I'm not going through 1 bar, I'm going through 2 per stirrup, right? Same thing here, so I'd be going through a bar here and a bar here, right? Now, what we have in this image are sometimes what are called either hoop stirrups or U-shaped stirrups. Like I drew U-shaped stirrups right here on the board, okay? If I look at this cracked region, how many bars would I be cutting through in a given stirrup across a shear crack? I'd be cutting through 2, right? So in this region, or in this term, when I'm trying to compute AV, it's not the area of a bar, it's 2 times the area of a bar. So, a very common stirrup size is a number 3. Number 3 stirrups are very, very common. The area of a single number 3 bar is 0.11 square inches. If I tell you I'm using number 3 U-shaped stirrups, I don't use 0.11 as AV. I use 0.22 because there's 2 bars going across that crack. Does that make sense? Here's another way of looking at it. What if I start throwing out some really weird cases? So this case is what, these two cases is sort of what I have right here. The area in shear would be 2 times the area of a bar. 2 times the area of a bar. This one, I only have 1 stirrup, or 1 bar across the crack. So the AV would be 1 times the area of a bar. What about this one? 4. Okay? So when you use your AV term, make sure you're using the right value. Okay? Does that make sense? Okay. Now, a couple of notes regarding reinforcement. Number 1, ACI has some limits on the minimum amount of reinforcement that you can provide, just like they have limits on the minimum amount of reinforcement you can provide for bending. These are minimums on the limits for shear. Now, what we're going to do from a design standpoint, we're not really going to compute a minimum AV. Instead, what we're going to do is we're going to use this term to figure out what's our limit on spacing. Okay? We can still use a number 3 stirrup or a number 4 stirrup or whatever size stirrup that we want, but think the smaller the stirrup size, the more stringent the limit is going to be on how far apart we can space them. Okay? So this is going to sort of be our limit on spacing according to minimum reinforcement, and then there's also going to be a limit based off of our maximum spacing. Okay? And basically that's just a function of how much capacity we're getting out of the steel that we're providing. So that isn't going to mean a whole lot right now. These limits are going to mean a lot more from a design standpoint. They're going to mean a lot more when we're designing our stirrup layout. You may leave it here for a sec. I see a couple of folks writing. What can y'all say? All right, everybody good? Okay. Now, what I want to do is I want to assess the shear capacity of the following beam, and I want to show you what's going on here. I wasn't able to fit everything on one slide. So let's sort of take stock of what we got going on here. So I have a beam that's 4 KSI normal weight concrete. The FYT is 60 KSI. Now, just to be clear, what I'm talking about there is the yield strength of the stirrups, not the bars. If you notice, I didn't give you any information at all about those bars on the bottom, because quite frankly, I don't really care right now. I don't care about those bars, I care about the stirrups. One of the things about shear design, and I didn't really go into this earlier, but I should mention it while you're writing this down, shear design is always a known cross-section design problem. Shear design is always done after you've done moment design. So you've already figured out the shape of the beam and figured out the reinforcement in the beam, whether it's a T-beam or rectangle or whatever. Then you come back and do shear. It's sort of a, I don't want to say it's not an afterthought, but you do that after you've figured out everything else. Now we're going to say it's simply supported. It's 24 foot long, and number 3 stirrups are utilized. Now we're going to put 1.5 kips of dead load on there. We'll say that includes self-weight on it, guys. And then 3 kips per foot live load. Actually, I'll check the example, make sure. I'm pretty sure that includes self-weight. I can't remember that. Now, does everybody have this? Okay, now, I want to look at this. This is the stirrup layout across the span. Now, the stirrup layout across the span, one of the things about shear design is that if your loads and your geometry is symmetric, then your shear design will be symmetric. In other words, let me see if I can draw this up here. So I have a beam. So I have a support here and a support here. So see where it says region 1? So region 1, I'm using 4-inch spacing. I have 13 spaces all the way to here to 52 inches. Okay, so I might have 4-inch spacing here. I'm going to have 4-inch spacing here. So it's like a mirror image across the center line. So as you get to the center, it mirrors off of one another. You'll also notice with shear design, you tend to use tighter spacing near the supports and wider spacing near the center. And that's because that's what shear diagrams look like. I mean, if I have a simply supported beam and a uniformly distributed load, the shear diagram looks like that, right? If I have higher shears near the ends, very, very low shears in the middles. As a result, near the middle, I don't really need that many stirrups. And there will be a region near the center where no stirrups at all are required. But we'll get into the ACI requirements of that as we progress. Does everybody have this? Okay. Now let's just sort of get right into this. Now ultimately what we're going to generate is this image here. That's another thing about shear design. Shear design is a very visual process, so let's just sort of get right into it. I'm going to need your help on some things. So let's start off with the loads. So the dead load was 1.5 kips per foot. The live load was 3 kips per foot. Am I correct on that? Yeah. Okay, so what is the factored load? It's 1.2 times the dead plus 1.6 times the live, and that's what? Loads of fun. That's pretty good. 6.6. Say it again? 6.6. 6.6 kips per foot. And I'm saying, all right, now, let's determine a couple of things. Let's determine the reaction. Does anybody remember the reaction? Or how to determine the reaction of a simply supported beam uniformly distributed load?
WL squared over 2.
Not WL squared over 2, just WL over 2. So 6.6 kips per foot times, now how long was this, 24 feet? And what does that end up equaling in the end? $79.2 kips. Is that a fair assessment? All right. Now, part of the purpose of this problem is to remind everybody about some fundamentals of structural analysis. One of the other trickier aspects of this topic is this topic, above all others, probably borrows upon your understanding of CD 312 more than others. What do I mean by that? Here's the beam. It is being subjected to what? 6.6 kips per foot? Is that what you said? And then the reactions, 79.2 kips. And then this dimension is 24 foot. Is that what you said? All right. So what's the secret weapon of structural engineering? A samurai sword or lightsaber if you happen to be a sci-fi fan. Don't know how everybody feels about episode 9. I haven't watched it yet, so no spoilers. So we're going to cut a section at some distance x, right? So let's cut a section. Let's see if y'all remember this. When you cut a section and the distance is x, do you look towards the origin or away from the origin? Towards the origin. It's easier. The math is easier. So what do we have? We have been a while, hasn't it? All right, so this is, oh. Now remember, we have an unknown shear and an unknown moment. I don't really care about the moment, I just care about the shear. So this is 6.6 kips per foot. And then what do? I take that and I collapse that into a single point load. How much is that point load?
6.6x.
6.6x. Now we could go ahead and put here that that is x over 2, but again, that doesn't really matter. The only reason why that would matter is if we were interested in moment, force times the moment arm. But in the interest of being complete and comprehensive, why not go ahead and list it there? Now, if I want to determine V, what do? I sum forces in the y direction. Right? And so I got 79.2 going up, 6.6x going down, V going down. So 79.2 equals V plus 6.6x, or V equals 79.2 minus 6.6x. Or if we want to be, I guess consistent in our notation, VU as a function of x is 79.2 kips minus 6.6 kips per foot times x. Is that shaking off some cobwebs? That stuff we're going to need to be doing a lot, okay? Because shear design means, like, one of the trickiest parts of shear design, I'd argue the tricky part of shear design, is that you need to understand the shears not just at a given point, but along the span. And that means deriving equations for shear, okay? Now you can always test this equation out by Excel. So what do I mean by that? Does everybody have this? Okay. So, how long's the beam? How long?
24 foot.
So, if I were to zoom out, something like that. Now, what was the equation again? 79.2 minus what?
6.6x.
All right, so equals that look like a shear diagram? Looks like one to me, right? Remember, you can get a little fancy with it. You can say that needs to go from 0 to 24. 3. Show the labels bottom. You know what I'm talking about, right? Hopefully this stuff right here is child's play. Is everybody okay with doing all of that? I hope. Okay? So that's what our shear diagram looks like, but let's be clear. That is the diagram representing the loads, okay? The force on the beam, okay? Now, one of the things that you'll find from a shear perspective, we've got positive shears and negative shears. What does that mean? Like, what does that physically actually mean when I say positive versus negative shears? Well, it means, am I taking the beam and shearing it this way, or am I shearing it this way? Now, does that really matter in terms of how the beam performs? Not really. Bending does matter, because whether or not I bend it this way or bend it that way, that affects whether or not the top is in tension or the bottom is in tension. And that matters because if the top's in tension, I need to put my bending reinforcement on top. If the bottom's in tension, I need to put the bending reinforcement on the bottom. So sign conventions for moment matter, but for shear, they don't. Okay? So from a shear perspective, the sign convention doesn't matter. So if that's the case, and since the beam is symmetric, I really only care about half of this shear diagram. A lot of times when we plot shear diagrams, we only care about half of it. We only care from here to midspan. That only works when the beam is geometrically symmetric and the loads are symmetric as well. Now, we're not going to have time to finish this, so we're going to do this next time, but I want to show you something. So here's the beam, here's this. I want to look at this image right here. So what I have here is an image showing the loads and the resistances. Okay? Now, notice how the resistance, there's a couple things to notice. See how it's kind of stair-stepped? Okay? The reason it's stair-stepped is because I've got 4 regions. For each of those regions, 1, 2, 3, 4, I have a separate capacity. That's point 1. But number 2, notice how the resistance curve is above the blue curve. What that means is that this beam on average, or not on average, it does, has more resistance than it does loads. So what does that mean? That means the beam is safe. That means it has more strength than the loads it's being subjected to. So on Wednesday, what we're going to do is we're going to finish this plot. Then we're going to ask, well, how do we design? Okay? Designing is not hard, but it is iterative and it is very, very graphical. You have to construct these shear diagrams kind of by hand, and they can get a little intricate when you look at the various regions. But we'll talk about that on Wednesday. I'm going to leave it here. That's all I've got, everybody. So you steel folks, I'll see you in a couple minutes. Everybody else, see you on Wednesday.